One.
This is Larry Moore. I'd like to welcome you back to our presentation number 14 in our biological wastewater treatment training series. Today we'll be using the BioTiger model in Department of Energy's MEASUR suite of software packages. And today this will be case study number 1. And we're going to be looking at a military wastewater treatment plant and evaluating it for potential energy savings. So let's just call it military-based wastewater treatment plant. The plant was designed as a conventional activated sludge process, and as we'll see later, because it's operating in such an underloaded condition, it's actually operating as an extended aeration activated sludge plant. But we'll just keep that in mind as we go through the analysis. Their preliminary treatment consists of screening and aerated grit removal. Then they come out of the grit chamber and go through some pre-aeration tanks. Then, because it's a plug flow activated sludge conventional plant, that's how it was designed, they included primary clarifiers. They have 3 primary clarifiers, and they're only using one of those right now. But they're getting excellent BOD and solid removal across the primary clarifier. And then they come out of the primary clarifier and enter 2 aeration tanks, which is how many they have. They have flexible membrane fine bubble diffusers that they put in a few years ago. And then they come out of the aeration tanks, go into 4 secondary clarifiers, then into a chlorine contact basin, and then they discharge the effluent to the receiving stream. So that gives you a little background on the treatment plant. All right, let's look at the design parameters for this plant. It was designed for 2.5 MGD and fairly strong wastewater, 250 BOD, 350 suspended solids, TKN of 45, and ammonia of 25. So it's almost high strength municipal type wastewater. And because they discharge to a relatively small stream that has a real low flow in the summer they have very stringent limits. Now in the winter, the stream flow is much higher, and you can see their winter limits are more like secondary treatment. But because they're under low flow conditions, they're about 22% of the total stream flow under summer low flow conditions. Then we have fairly stringent limits, 12 CBOD, 30 suspended solids, and 3 ammonia and nitrogen. The plant again is designed for 2.5 MGD, but it's only getting 0.58 MGD. So it's operating at about 23% of design capacity. So it's very underloaded. You have both aeration tanks in service, a total of 0.66 million gallons aeration volume. Primary clarifiers again remove a lot of the BOD. It's only 90 milligrams per liter going to the aeration tanks. And then the solids also very good removal in the primary clarifiers. The solids are only 100 milligrams per liter going to the activated sludge reactor. And again, it was designed for conventional plug flow. And it still is a plug flow reactor, but because of the underloaded condition and using all of the aeration capacity available, they're basically operating as an extended aeration activated sludge plant. As I said, a few years ago, they put in fine bubble diffusers. The old diffusers were coarse bubble, and fine bubble diffusers are approximately 50% more efficient than coarse bubble. And they have 3 60 horsepower positive displacement blowers. They only need to run 1, and they run it 22 to 24 hours a day. And it's and then they operate an MLSS concentration of about 3,500 milligrams per liter. Here's a picture of the 2 aeration tanks. They look real good. You can see just a moderate amount of foam, maybe a little darker chocolate brown color than we'd normally expect, and that's because they have a very old sludge. But the plant's working very well, producing excellent effluent quality. So again, we have one 60 horsepower positive displacement blower that supplies air to the aeration basin, and that blower runs at 100%, 22 to 24 hours a day. They have a couple of aerobic digesters to digest the waste primary sludge and the waste activated sludge. And they run one 75 horsepower positive displacement blower 24 hours a day in the aerobic digester. Now, we can't analyze aerobic digestion with BioTiger, but we will analyze it at the end to show you some additional energy savings in the aerobic digestion process. But according to my calculations, they will destroy, the way the digester is operating, they'll destroy about 390 pounds per day of volatile suspended solids in the aerobic digesters. And all of that destruction of solids is because of the primary sludge. Because they're operating such a long sludge age in the activated sludge, the sludge is already well oxidized when it comes out of the activated sludge process, so it doesn't need any additional oxygen. It's fully oxidized. But we need 2.3 pounds of oxygen per pound of VSS destroyed in an aerobic digester to satisfy our oxygen requirements. So if you multiply 2.3 times 390 pounds per day, then we need about 900 pounds per day of oxygen in the aerobic digester. So we'll talk about that again as a last option as far as energy savings for this plant. Their current energy use is 86,000 kilowatt hours a month. And again, we like to normalize it to see kind of how they compare to a typical plant. So if we divide 86,000 kilowatt hours a month by 30 to get kilowatt hours per day, and then divide by 0.58 MGD, they're using almost 5,000 kilowatt hours per million gallons of wastewater treated. In a typical conventional activated sludge plant, we would expect them to use 1,800 kilowatt hours per million gallons. That's a ballpark estimate, but that's what we expect a conventional plant to do. So we look at them versus the conventional plant, they're using 172% more energy than a typical conventional plant. So we should have a great opportunity to save some energy here. And another thing, because they're operating in such a long sludge age, they're doing an excellent job of nitrification. The wastewater is fairly low in alkalinity, so they have to add soda ash to provide adequate alkalinity for biological nitrification, and they're spending about $15,000 a year doing that. And we'll talk more about how we can help them with those chemical costs as well. So the way the blowers are working now and operating at a DO concentration in the two basins at about 4.5 milligrams per liter. Now, again, these are plug flow reactors, and they have tapered aeration, which means they have more aeration at the front of the reactor. It decreases as you go along the length of the reactor, and the least amount of aeration at the end of the reactor. But the average DO in the basin is about 4.5 milligrams per liter, which is way more than we need. We really only need about 1.5 to 2. So again, what that does, that reduces the efficiency of our aeration system. The RAS rate about 0.66 MGD, WAS flow rate 0.0018, and their sludge coming off bottom of clarifiers has a solids concentration of about 6,500 milligrams per liter. As I said before, they get outstanding effluent quality, about 3 milligrams per liter, CBOD5, 4 milligrams per liter suspended solids, ammonia about 0.1. The nitrates going out in the effluent fairly high, 30 milligrams per liter, and TKN about 1 milligram per liter. So the total nitrogen will be the sum of the NOx concentration and the TKN concentration. 30 plus 1 gives us total nitrogen going out in effluent, 31 milligrams per liter. Now, what we want to recognize here is this high amount of nitrate nitrogen, mostly nitrate going out in the effluent. That's a lot of available oxygen that if we create an anoxic environment in the process in some way, then we have enough oxygen there in the nitrates to actually reduce the oxygen requirements for the aeration system about 25%. So we'll certainly want to take advantage of all those nitrates going out in the effluent. So let's look at, first of all, at energy conservation measure number one. Again, we're operating about 23% of design capacity. And when we met with them and sat down that day, I pulled out my BioTiger model. We put it on a TV screen in their control room. And at this particular military base, they had a contract operator. I didn't know how cooperative they would be, but they were very receptive when I showed them with my model exactly what we could do to help them save energy, because they save energy, then that's, for the contract operator, then that's money in their pocket. So I said, look, guys, we don't need to run both aeration basins. We should be able to do fine with one. And then also we can run the blower less than what it's being run today. You're running about 22 to 24 hours a day. We can cut down on the blower runtime. So we got a lot of opportunity for savings here. And we didn't look at this. I would have done this as a second step. Again, I didn't want to push my luck and ask them for too much. I was just hoping they would consider going to one aeration basin and operating the blower a little bit less each day. But as we'll see in a moment, when we look at another energy measure, we can actually run that blower at 60% speed, and we can reduce the MLSS concentration from 3,500 milligrams per liter down to 2,500 milligrams per liter, reduce their sludge age even further, and make the process even more efficient. And then finally, the third measure we looked at is the use of, right now they're using that 75 horsepower positive displacement blower 24 hours a day. According to my calculations, again, they needed 900 pounds a day of oxygen from that 75 horsepower blower. The way they were operating it, the blower essentially was supplying the equivalent of 1,950 pounds per day. So if you divide the 900 pounds divided by 950 pounds per day, then we see that we should be able to run that blower only 11 hours per day and satisfy the oxygen requirements in the digester. All right, so let's get out of this now, and we want to get into measure. And we're going to measure. We want to create wastewater assessment, and we're going to name this assessment. We'll call it, I won't be too creative here, military base wastewater treatment plant. And we're going to add an assessment. Okay, so again, we come into system basics. We want to use US dollars, imperial units. And because this plant, as I did the initial calculation, was operating at a sludge age of over 100 days, we're going to need to make the maximum solid retention time about 200 days so that we analyze and are able to look at their situation. We only analyzed a 100-day SRT, then they're operating outside that range, and so that wouldn't be worthwhile. So in this case, we're going to operate with an SRT up to 200 days in our analysis. Click off the sign there, and we'll click to next here, and then we get into our activated sludge data. So we're going to look first of all at existing conditions. Let's analyze at a temperature of 20 degrees C. So that would basically be a temperature we'd expect in spring or fall. The BOD coming into the aeration basin, 90 milligrams per liter. Under current conditions, they got 0.66 volume, million gallons of aeration volume. The flow rate is only 0.58 MGD. Now the inert VSS, because the suspended solids coming into the activated sludge process is so low, I went with a very low inert VSS of about 10 milligrams per liter. Their influent TKN to the activated sludge process, about 35 milligrams per liter. As always, I'm going to use 0.85 for the VS TSS ratio of the biomass. We got 100 milligram per liter suspended solids going to activated sludge. And again, with that low solids loading to the activated sludge, I'm only going to use 5 milligrams per liter of inorganic solids going to the aeration tanks. They're producing about 4 milligrams per liter suspended solids in the effluent. Again, we have to provide that information to the model. Their RAS TSS was 6,500 milligrams per liter. And then, as I said, we have the option to use as our control MLSS or SRT. Well, again, this plant, they're using MLSS, and they said we try to operate the plant at 3,500 milligrams per liter. And as normal, I'll use the conventional parameters for the biokinetic constants. Let's go with next. Then we get into aerator performance. They told me they were running about a 4.5 DO on average in the aeration basin. These are standard numbers for alpha and beta, 0.84, 0.92. That's what I generally use. And they're using fine bubble diffusers, flexible membrane fine bubble diffusers that I said they put in just a few years ago. And selecting that type of aeration, our standard oxygen transfer rate, 3.1 pounds per horsepower hour, which is really good. They're operating a 60 horsepower blower, and the site elevation at this particular site is 320 feet. And they told me they run the blower about 22 to 24 hours a day. So I was conservative. I said, well, let's go with 22. It's a positive displacement blower, and it's running at 100% speed. And then they said they pay 7.5 cents. They had a very good energy rate, 7.5 cents or $0.075 per kilowatt hour. And again, that includes demand charge, environmental fee, administrative fee, power factor penalties, everything, taxes. That's the overall charge they're paying. And they're operating fully aerobically, so there is no anoxic zone. So now we want to get into assessment. And we've got our conditions defined for the current conditions. Now we want to add modified conditions. And we're going to, in our alternate scenario, we're going to operate with one aeration basin in service. Since we got caps there, let's cap this. One aeration basin. So that's going to be our alternate scenario. And we're also going to run the blower less time. So temperature's still the same, loading's the same. Now, instead of using 2 aeration basins, we're going to use 1. So we're only going to use 0.33 million gallons of aeration volume. Influent flow rate stays the same. All these other values coming in are still the same. We're going to assume we can still produce 4 milligrams per liter suspended solids in the effluent. And we're going to continue to operate at 3,500 MLSS and assume the RAS TSS will stay at 6,500. We'll leave our biokinetic constants where they are. And so let's look at aerator performance. So again, initially, and under current conditions, 60 horsepower blower, 22 hours a day, 100% speed. And under those conditions, the oxygen requirements in the process are about 1,300 pounds per day. Operating at 4.5 DO, they're supplying 1,400 pounds per day. So these really should match. So what we're going to do, I'm going to bump the DO up a little bit to get the O2 supply down. So let's bump the dissolved oxygen concentration up to 4.8 and see how that works. Well, that dropped the oxygen supply down to 1,304, almost exactly what they need. So according to the model, they should be operating at about 4.8 DO, and that's pretty close to what they told me. So existing conditions are pretty much optimized now. Now let's look at our one aeration basin. I said, I think we can, what we want to do is create an anoxic zone in your reactor. So instead of, we're going to turn the blower off for 8 hours a day. We're only going to run it 16 hours a day instead of 22. And right now we'll stay with 100% speed because they don't have a VFD. We'll talk more about that later. And electricity cost is the same. But now by turning that blower off for up to 8 hours a day, we're going to create an anoxic zone throughout the reactor. So now we're going to answer this question. Yes, we have just created an anoxic zone by turning our blower off up to about 8 hours a day. And to get their buy-in to these pretty significant changes to this plant, and again, I'd never met these guys before we sat down that day, so they didn't know me from Adam. So I said, look, let's just do this gradually. Let's go to 20 hours a day operation for a few weeks, and then let's go to maybe 18 or whatever, and then gradually down to 16 hours a day, just to make sure that it's going to work like I say it's going to work. So we do that, and of course, D up here is 4.5. So our oxygen requirements now have dropped from 1,300 to a little less than 1,000 pounds a day. And the reason for that is because now we're denitrifying and we're using a lot of those 30 milligram per liter nitrates that are going out in the effluent. And we're going to, again, reduce our oxygen requirements right at about 25%, which is excellent. But at a 4.5 DO, we're still supplying a little bit more oxygen than we need. So let's click optimize here and let it find out what's the actual DO. Okay, so the actual DO, only operating our blower 16 hours a day and cutting our aeration volume in half, we still are going to have way too much oxygen in our aeration basin, but let's go ahead and analyze it under this scenario. And so we've got things pretty much optimized. And what we see is by going to one aeration basin and running that blower 16 hours a day versus 22 hours a day, we're saving 27% on their aeration energy costs. So if we look at energy savings, their energy cost now is about $23,000 a year. Again, this is a fairly small plant, only treating 0.58 MGD. And but the energy cost by turning that blower off another 6 hours a day should be somewhere around $17,000. So the energy savings are about $6,000 per year. Okay. Now we were able to get additional energy savings. Number one, again, I told him, said, look, you don't need to run your aerobic digester blower 24 hours a day. You only need to run it 12 hours a day. And so they implemented that. And by doing that, running that 75 horsepower positive displacement blower only 12 hours a day versus 24 hours a day, that saved them another $15,000 a year in energy. And then another benefit, when we created this anoxic zone by turning the blower off 8 hours a day, we reduced our oxygen requirements, and we also generated a significant amount of alkalinity. For every pound of nitrate nitrogen we convert to nitrogen gas, we generate 4.57 pounds of alkalinity. So what happened was, by operating in this mode, they were able to completely eliminate the addition of soda ash. They were spending $15,000 a year adding soda ash to the activated sludge process. They were able to essentially eliminate that, and that saved them another $15,000 a year. So the energy savings, coupled with the energy savings in activated sludge, about $6,000, $15,000 in the digester, that's $21,000, and then add in the $15,000 a year in chemical savings, we were able to save these contract operators about $36,000 a year. Now, if I'd had an opportunity to go back and visit this plant again, I would like to optimize even further. And you say, Larry, you mean we save more? Yeah, we can save more. Why? Because we're running still at almost 4.7 milligrams per liter of DO. We've dropped our SRT from 162 days, which is way too long. By running one aeration basin, we cut it more than half, got it down to about 70 days. So to to try to optimize this plant, what I would like to do, first of all, I would like to reduce the MLSS concentration. We don't need to run at 3,500. We should be able to run at 2,500 because it's in such an underloaded condition. So I'm gonna go back and make that change back in the activated sludge assessment component. Go back to aerator performance, and we don't need to run that blower at 100% speed. We can run it at 60% speed and satisfy the oxygen that we need. So again, we're going to only run it 16 hours a day, 60% speed. So you see, if we look down here at the oxygen required, again, 965 pounds a day. And it's, oh my goodness, we're only supplying 600 pounds a day. But let's go back. That's operating at a DO of 4.66. So now that we've changed the conditions and running that blower only 60% speed, we're going to get that DO down to a level that's going to make it much more efficient. So all we got to do is click right here and optimize DO, and it's going to tell us the DO that we'll be operating at, and it's running that blower at 60% speed. So we click it, and so what we see by running the blower at 60% speed, still for 16 hours a day, we have dropped the DO from about 4.6 or 4.8, whatever it was, down to 2.4, which is much better. And by reducing the MLSS from 3,500 to 2,500, now we've taken that, and then the first change, going to one aeration basin, has dropped it to 70, but changing it to 2,500 MLSS, that got our SRT down to 45, which is still, you're in the extended aeration range, so we still got plenty of SRT. The plant's going to perform really well. It actually should perform better at 45-day SRT instead of 162-day SRT. So we've essentially reduced their sludge age by about 70% or so. And I would argue, and I think they would tell you that their plant actually ran a lot better. So by cutting the blower speed back to 60%, it allowed us to save another $6,700. So remember, savings before were about $6,300. By now running the blower at 60% speed, our total energy savings would be about $13,000. So again, we didn't get into this, but if I had an opportunity, as I said, to try to optimize this plant even more, this is something that we definitely want to do. Now, they don't have VFD, so what I looked into, the cost of a VFD for a 60 horsepower positive displacement blower, I believe would be somewhere around $8,000, $9,000. And so with a payback, again, we got an additional $6,700 a year savings by running at 60% speed versus 100% speed. And so that we could pay for that VFD in about 14 to 16 months, depending on whether it costs $8,000 or $9,000. So that's an excellent payback. So again, we didn't go into this because, again, I never went back and made another trip, and I didn't want to, again, push my luck. We didn't want to make too many changes. I was just trying to build up their confidence initially in making the change from 2 aeration basins to 1. So that's it in a nutshell for this military-based wastewater treatment plant. As I found out later, we had a training seminar, and they came and gave a testimony of how this worked out. They were actually able to save more energy than what I had originally anticipated, and they were real pleased. The plant continued to run extremely well, and they cut their operating costs again about $36,000 a year. So they were real happy with these changes in the plant. So appreciate you listening today. And this is again presentation number 14, case study number 1. And our next case study will be our next presentation will be our final presentation, presentation number 15. And we'll be looking at an extended aeration municipal wastewater treatment plant. And we'll call that case study number 2. So have a great day, and I hope to see you for presentation number 15 real soon. Thank you.